Yes, the ABC of galaxy evolution. So I hope to convince you that although a lot of astrophysics is quite complicated, you can occasionally boil things down to the ABC. When we look out into the universe, we see beautiful structures. We see these wonderful galaxies, many of which are spiral in their structure, and some of them have beautiful spiral arms. Some of them appear to be interacting with some of their neighbors. So you get the beautiful rose galaxy here, where one seems to be upsetting the other. There's some gravitational to and fro between the two galaxies. And some of them are beautiful face-on galaxies, and we see that again, there's beautiful spiral arms, and sometimes we see interesting structures where the spiral arms don't seem to come from the center of the galaxy, but come from a bar. The bottom line is that every galaxy is different, and there's an awful lot of galaxies out there. When we look into what we can see of the universe, the so-called observable universe, there might be something like 1 trillion galaxies. Hubble has looked at a few of them, but only a few thousand or a few tens of thousands. But we think there's perhaps 1 trillion out there. And maybe, just like snowflakes, they're all different. But we can ask ourselves, how did these structures come to be? How do we end up in a universe full of galaxies? So I'm going to be talking about the ABC, and I would argue that you can reduce most of what we need to understand about galaxies. Probably a lot of astrophysicists would disagree, but I would say you can reduce a lot of what you need to know down to the ABC. The A stands for accretion, which means that galaxies were formed in the very early universe by matter accreting. The Big Bang created a shed load of hydrogen. All the hydrogen that's been burning in stars for the last 13.8 billion years was made in the first 3 minutes of the Big Bang. That hydrogen has been dispersed throughout space, and ever since, gravity has been accreting all of the gas that's out there, forming stars and forming galaxies. So A is for accretion, or if you prefer, accumulation of matter under the influence of gravity. The B of the ABC stands for black holes, because we think at the center of every galaxy there appears to be an enormous so-called supermassive black hole. Supermassive just means it's got a lot more mass than, for instance, the mass of our sun. Not just a few times the mass of our sun, but probably millions, if not billions times the mass of our sun. It looks like there's a black hole at the center of every galaxy. Some of them are voraciously eating all the stars and gas around them. The one in the center of our galaxy appears to be quiet. It doesn't appear to be feeding. It doesn't appear to be pulling in a lot of gas around it. So it doesn't seem to be doing much. Other galaxies are much more active. And the C of the ABC stands for collisions, because in terms of evolution of galaxies, they might be born from gravity simply pulling stuff together. But the reasons galaxies now don't look the same as galaxies billions of years ago is because for billions of years, galaxies have been colliding with each other. You tend to think perhaps as one galaxy as being something completely isolated from all the other galaxies in the sky, just like you think of stars being isolated from each other. Each might have their own planetary system, but effectively the stars are all separate. We might think of galaxies the same way, but in fact, the collisions and mergers of galaxies have been an essential part of how galaxies have evolved over billions of years. So where does the story start? Well, in a sense, the story starts, well, like all good stories, it starts at the beginning. Let me get my universe out of the box. I always carry the universe with me every once in a while. So at the beginning of everything, given that we know the universe is expanding, and at the moment all the galaxies are billions, if not tens of billions of light years apart, the entire observable universe at the moment is 100 billion light years across. But we know the universe is expanding, so if we wind the clock back, we come to the conclusion that everything used to be a lot closer together. And things that are now hundreds of billions of light years apart used to be separated by centimeters, if you wind the clock back far enough. So that's why I tend to think of the early universe as being a golf ball, because if you go back far enough, everything used to be a few centimeters apart that we see now in the observable universe, separated by enormous distances. Sorry, my universe seems to be... Stay. It's not going to, is it? Oh, yes, it is. You're spending more time watching that than you are listening to me, aren't you? The universe expanded from the golf ball, and at some point it changed from being opaque to being transparent. Once the universe turned transparent, all of the light that was bouncing around inside was released, and that's what we see in the cosmic microwave background. Wherever we look, there's a microwave glow in the sky. That, if you like, is the afterglow of the Big Bang. And because the original golf ball of the early universe had a number of dimples in it, not quite dimples in the same sense as the golf ball, but variations in density, those have now imprinted themselves on the cosmic microwave background, and the universe has continued expanding, and gravity has started to grab hold of these density variations, some parts of the universe being slightly more dense than others, and that has given rise to the structures that we see today. When we look out into the universe with the Hubble Space Telescope, this is obviously a very small patch of sky. The Hubble Space Telescope can't see large chunks of sky at any given time. It's looking at a tiny bit of sky, much, much, much smaller than would be covered by your little fingernail at arm's length, and yet it's seeing thousands of galaxies. So we can ask the question, how exactly do we get from the golf ball or the cosmic microwave background when the universe was very young to something which looks like this, where we have trillions of galaxies out there? Don't worry about the detail on the picture on the left. This is simply to remind us that a lot of our understanding of how the universe has ended up the way it is not all based on observation. We can see galaxies, but that doesn't necessarily tell us where the galaxies came from. A lot of our understanding is based on the fact that for the last 10, 20, 30 years, we've been doing a lot of simulations to try and calculate how might the universe have evolved from the Big Bang to the state we're in today. And it's these computer simulations that allow us to get a handle. Can we set up in a computer program all the laws of physics as we understand them, how gravity works, how light works, how nuclear reactions take place, etc.? Can we build all of that physics into a simulation and then run that simulation to see if we end up with a universe that looks like the one in which we appear to be living? So I'm going to be using just a few of these simulations. There are lots around, lots of different research groups all over the world are running very complex computer programs on supercomputers. I'm just going to take some illustrations from a particular set of them. It's called the Illustris simulations. We don't need to worry about why they're called that. There are lots of them around. I'm just using a few pictures and videos from this particular set. And one of the simulations starts with, if we imagine the very early universe where we have a whole load of hydrogen and we have some density variation analogous to the dimples in the golf ball, if we have some variations in the density of the gas in the early universe, can we see what gravity would do to that? So this simulation is start with a large bit of the universe, not the entire universe, but a fairly large chunk of it, fill it with gas, put in a little bit of variation. If it was perfectly uniform, nothing would happen. So you put in slight variations. Perhaps you can see it's just a slightly different shade of grey in a few different blotches on this image. We put that into the computer simulation and we just let gravity do its stuff. And we see what happens. And the denser bits get even more dense and the less dense bit get less dense. And we end up forming a structure simply under the influence of gravity, and we start forming this so-called web structure. You can see these filaments. It's not perfectly uniform by any means. We get some regions of space which appear to have very little in it, and we get other regions in which we get filaments, and where these filaments seem to cross each other, we get these high density regions which show up white in this particular simulation. These are the places where galaxies and clusters of galaxies and superclusters of galaxies are forming, simply because gravity is pulling everything together, and if we start with small variations, those variations get exaggerated as time goes by. And it didn't say so, but this simulation has been running for, let's say, a few billion years. In other words, that's roughly what we actually see. If we look out into the universe and try and figure out where are all the galaxies, we don't find that all the galaxies are uniformly distributed throughout space. We find the galaxies do appear to be clustered with a large group over here and a large group over there, and sometimes the galaxies seem to be stretched out along these filaments. In other words, although this is a simulation, what we've ended up with is a structure that looks very like the actual structure of the universe in which we live. This gives us some confidence that these simulations are actually telling us something real. They are not just fanciful computer simulations which mean nothing. They do seem to indicate that we can get an understanding of how the universe ends up with this particular structure. So we think what's actually happening is, again, this is a slightly different still from the same sort of simulation. The hot spots, the bright spots here, are the places where galaxies are forming. And what we think is happening is the densest parts of these filaments are forming galaxies and clusters of galaxies, and the matter that is forming these galaxies is actually streaming down these filaments. We're not going to go into the details of these simulations, but it is thought that these galaxies start to form, matter starts to get compressed into certain regions, and the more you compress the matter, the more gravitational pull it has, the more matter comes streaming down these filaments from various directions and builds up these galaxies and clusters of galaxies. So you could argue that this particular picture is a set of proto-galaxies. It's all the matter we need to start forming galaxies. But there's a catch, because it's never quite as simple as you would hope. And the catch is, once you start actually forming stars, strange things start to happen. Because once you start making stars, stars are born, stars live, and stars die. And when stars come to the end of their life, they can go supernova or form black holes, and you can end up with a lot of energy pouring out of these regions in which gravity is trying to pull matter together. So because you end up with a lot of radiation outflow when you actually generate stars, when you start making stars, or once stars actually start dying, you can actually produce enough radiation pushing out that you actually stop matter falling in. So when you're trying to pull matter together to make stars and make galaxies, it's always a balance between gravity trying to pull it in and radiation pushing out. And if you don't get the physics right of how do you make stars and how do stars live, then you can't understand how galaxies start to form. What we would like to do is to understand why we get such a variety of galaxies. These are actual galaxies that have been imaged, and they've been put together in this grid just to show you that all galaxies are different. The ones that are a little more bluish are on the left-hand side. Those are the ones that usually have a disk-like appearance, quite often spiral galaxies. Galaxies that appear redder and have less structure, so-called elliptical galaxies, which look more like rugby balls rather than spirals, they're over on the right-hand side. But there's a huge variation in the structure, not only just the size, but in the structure and the color of galaxies. And it would be great if our simulations managed to reproduce this sort of diversity that we see in the universe. So let's have a look at the first of the ABC. We believe that galaxies form from accretion, so let's look in a little more detail at how that actually happens. Before we look at the simulation itself, let me just say a little bit about how the simulations were actually carried out. The Illustris project is this project whereby a number of rather clever people have set up the code to run the simulation, taking into account what the stars are doing, what gravity is doing, etc. And they're trying to run the simulation from the Big Bang to the present day. The catch being they have to take all sorts of other things into account. They have to account for the fact that stars are being born and go supernova and generate black holes. They have to account for the fact that the universe is not only full of hydrogen and helium born in the Big Bang, but it seems to be also full of a rather enigmatic substance called dark matter. We think dark matter is out there. We don't really know what it is, but there appears to be more dark matter than ordinary matter, hydrogen, helium, etc. So that has to be taken into account in the simulations as well. So it's not just a question of accrete under gravity. We accrete under gravity, taking into account the fact that basically the stars push back with radiation from supernova, from black holes. The simulation itself, the first set of simulations of the Illustris project, ran, as you can see, in the early teenies from 2013 to 2015, and the computer code ran for 20 million CPU hours. So in other words, 20,000 1,000 computers would take 1,000 hours to do the calculation. The bigger the computer you use, the shorter the run can be. Once they did that, they realized they hadn't done the simulation quite as well as they could have. They figured out how to make it better. So they followed that up a few years later with a more sophisticated simulation. What do you think they would call that? Would that be Illustris version 2? That would be sensible. No, because they were Star Trek fans, they called it Illustris The Next Generation. So this has become known as Illustris TNG. The acronym at the top is what I'll use. It's often just abbreviated to TNG because everybody in the know realizes this means this particular series of Illustris simulations. The Illustris TNG simulations ran for 200 million CPU hours over that particular period of a few years ago, just pre-COVID. And of course, they don't run them on a desktop computer, they run them on a supercomputer with as many individual CPUs, computing processing units, as they can possibly get hold of. To give you an idea, if you ran this simulation on the fastest desktop you could get your hands on, the program would take something like 20,000 years to run. So you do need a supercomputer if you want this to run in a matter of months rather than in a matter of thousands of years. So it takes a bit of expense to get time on these supercomputers, but that's one of the reasons these supercomputers were built, is to allow you to do simulations like this. The simulations were done on different scales. You don't take the entire universe and trying to simulate it all in one go. If you're interested in a bit of detail about how a galaxy evolves, then running a simulation of the entire universe with 1 trillion galaxies would be far too expensive in terms of computing time to do. So they did calculations, they did simulations on various spatial scales. And because they're astrophysicists, they work not in light years, but in parsecs, which I'll come back to in just a second. So the TNG simulations operated on spatial scales of 300 megaparsecs or 100 megaparsecs or 50 megaparsecs, depending on, do you want the big picture or do you want the detail? And they ran it at various scales to try and make sure everything hung together. And just a point on parsecs, because not everybody is happy with them. 1 parsec is a unit of distance, which is approximately 3 light years. Astronomers, especially amateurs, tend to prefer to use light years because it's something you can get a handle on. If you know the speed of light, how far does light go in a year? That's a light year. Astrophysicists tend to prefer using parsecs for reasons we're not going to go into. The conversion is roughly a factor of 3. But one thing to bear in mind is parsec is roughly speaking the distance between stars. Not quite, but close enough. The average distance between stars is of order a parsec. The size of the Milky Way galaxy is 150,000 light years, or about 50,000 parsecs. And a useful yardstick, if you like, the distance between the Milky Way galaxy and the Andromeda galaxy is about 2 and a bit million light years, or about a megaparsec. So if nothing else, don't worry about parsecs, just remember that a megaparsec is roughly the distance between galaxies. It just happens to be the distance between us and the Andromeda galaxy. Okay, so let's have a look at what the simulation actually produced. Here we're looking at one of the bright spots that we saw in the earlier simulation. So matter is flowing down the filament towards this structure, and matter is flowing in from the bottom left, and matter is flowing in from the bottom right, and is starting to collect in this region of space. You can see the scale on the left-hand side. This simulation is running over a few billion years. So matter is streaming down from these filaments that were made by gravity pulling on all of these small variations in the original cosmic golf ball. And you can see that we're starting to collect a lot of matter in the middle there. Yellow means dense and hot, compared to light purple or dark, meaning relatively low density or relatively low temperature. So you can see that it doesn't all simply go to one point and make a gigantic black hole. It starts to swirl. Much like water going down a plug hole doesn't instantly go down the plug hole, it tends to swirl around before actually going down. And you can see that after a while, this region in the corners is now very dark because a lot of the matter is now ended up in this structure in the middle, which is starting to look a little bit like a spiral galaxy that we might recognize. Not quite, it's not quite old enough yet, but it's giving us the right sort of shape. And again, It doesn't all go to a point because all the matter coming down doesn't all try and get to the same point at the same time, so it ends up circulating to give us these sorts of characteristic spiral structures. Do we get the sort of structures that actually are representative of real galaxies? This is a simulation in the background. The black on white is just there to make it a little more easy to see what's going on. That's a large scale. TNG 300 is the largest scale simulation. And the question is, of all the structures that are generated, yes, we can see filaments and we can see lines that appear to be lines of galaxies. But if we zoom in on particular galaxies, do they look anything like the galaxies that we actually see in the universe? In other words, these 4 that happen to have been picked out, these 4 galaxies that appear in the simulation, do we see anything like that actually in the sky? And the answer is yes. For instance, this pair of galaxies that appear to be very close together at the top there, producing some tidal tails as they interact with each other, yes, we do occasionally see things like that. That's the antenna galaxy in the observation on the left-hand side. It looks suspiciously similar to the one in the simulation. And whenever we get interacting galaxies that get close enough to distort each other, yes, we do see galaxies that look like that out into the universe. And at the bottom, do we occasionally get galaxies that are relatively featureless with a few smaller galaxies around them? Well, yes, we do. We do indeed get that sort of structure. So it looks like the simulations are producing sensible-looking galaxies. But we shouldn't rely on a simulation at the largest scale. We should look at a simulation on a slightly smaller scale to effectively zoom in on some of the details. What if we were to go to not 300, but go to 50 megaparsecs? This is the smallest scale of those squares I showed you earlier. These are a number of simulated galaxies. On the left, the color shows you where the hydrogen ends up in the galaxy by following what the hydrogen molecules are actually doing, the hydrogen atoms are actually doing. And on the right-hand side, it's the same simulated galaxies, but asking the question, if that's where the hydrogen is, then we can work out how stars will form. We can calculate roughly how long a star lives for. And if we know where the hydrogen is, which is the main fuel for stars, we can work out where the stars will be and hence what the galaxy should look like. And that's on the right-hand side. And again, when we think about these galaxies on the right-hand side, these are all simulations, but anybody who's ever either looked at galaxies through a telescope or looked at the various images that Hubble has produced or various other telescopes have produced, we realize these all look very sensible in that they all seem to be the sort of structures that we do indeed see in the universe. And perhaps most importantly, we can ask, does the simulation generate galaxies similar to our own? Does it generate galaxies similar to the Milky Way? And yes, TNG 50, looking at the biggest, the most detailed view of the universe, does seem to simulate lots of galaxies with a mass of roughly 200 billion times the mass of our sun, indicating that there's something like 200 billion stars in that galaxy. Yes, that's about the mass of our Milky Way, and it does look a little like that. As far as we can tell, that is pretty much exactly what our Milky Way looks like face on. And if we were to look at the Milky Way from the side, it's basically like 2 fried eggs back to back, a little bit of a bulge in the middle, otherwise relatively disk-like. So yes, the simulations generate galaxies that not only that give us galaxies that look like the galaxies we see when we look out into the sky, it generates galaxies like the Milky Way. There's no reason to think the Milky Way is any way special, but it's good that it does generate the galaxy in which we live. So we have some confidence that it's doing the right thing. B is for black holes. What's going on in the center of galaxies? How do we know what's going on in the centers of galaxies? Well, if we look at the stars that are orbiting, it's rather tricky because the center of the galaxy is a very crowded area and there's a lot of dust there, which is why it's taken a while to actually get the data. But when we look at stars that are very close to the center of the galaxy, we see that they're orbiting in ellipses around something that we cannot see. The stars are in orbit, but their orbit is apparently around something that must be quite massive, otherwise the stars wouldn't be kept in their orbits, but we don't actually see anything there. If we follow that for a number of different stars, stars have been watched for many, many years to see how they're orbiting. They all seem to be orbiting one very small, invisible object right at the center of all those ellipses. So we come to the conclusion there is something very massive but very faint, basically invisible, at that particular location in the center of the galaxy. And because it's relatively easy to say if a star takes this many years to go round the object, what is the gravitational strength of that object? What must the mass of that object be to hold the stars in orbit? We can calculate that whatever that object is, it must have a mass of 4 million times the mass of our sun. This thing here, capital M circle dot, is just shorthand for the mass of our sun. Nothing special about the mass of our sun, it's just a convenient unit to use, rather than use kilograms or tons. So the object at the center of our galaxy is an object with a mass of 4 million times the mass of our sun, but it's relatively small. It can certainly be no larger than our solar system, only perhaps a few light hours or so in diameter. So we deduce one of the few objects that can have a mass that high but still not be very large. It can't be a star cluster because it would be far larger than the orbit of Pluto. And how else can you get 4 million stellar masses in such a small volume? So we think there is a so-called supermassive black hole, SMBH, in the center of our galaxy with a mass of 4 million solar masses. And as far as we can tell, every galaxy is the same. Perhaps not, but we certainly have evidence that a lot of galaxies, if not absolutely all of them, have a supermassive black hole at the core. They're not all the same mass. For instance, this one, Centaurus A, has a supermassive black hole of 100 million solar masses, not 4 million. It's a larger galaxy, and it appears to have a larger black hole at its core. And we think that's the basic trend, that the larger galaxies tend to have larger black holes. Anything that comes too close to a black hole is asking for trouble. So if a star happens to get close to a black hole, it's possible that the star gets completely and utterly shredded, depending on its distance. But again, remember, the material doesn't simply go straight into the black hole. It ends up circulating, again, like water going down from a bath through a plug hole. It doesn't all go down the plug hole in one go. It tends to circulate. And as it circulates, it gets hot. So this whirlpool effect here is called an accretion disk. Matter is trying to go down the black hole. The black hole is pulling it, but the matter is rubbing shoulders with all of the other particles of matter, the remnants of the star once it's been shredded. All of that is getting very, very hot. So the so-called accretion disk is a very hot disk which is radiating light of essentially all wavelengths, not just visible light. It can be radiating infrared and ultraviolet and X-rays. And rather enigmatically, we often get jets coming out of supermassive black holes via a mechanism which is still being researched. A lot of the energy of the infalling matter could get converted into energy, and that energy is used to generate these jets. We see the jets sometimes. This is a picture of the galaxy M87. There's the jet coming out. We can see it a little more clearly in a Hubble Space Telescope picture. There's the galaxy. We think there's a jet coming out in both directions, but one of those jets is coming towards us slightly, and the other jet is moving away from us, and it's brighter. The one that's pointing towards us is brighter than the one that's pointing away. So we don't tend to see the other one, but we do see this one. And in order to convince ourselves that these hypothetical concepts of accretion disks do indeed exist, they built the Event Horizon Telescope, which is basically join together lots of telescopes around the world and then take a radio image of the accretion disk, in this case the accretion disk around the galaxy, around the supermassive black hole in the galaxy M87. The black hole you can't see, of course. There's a shadow in the middle of this accretion disk. There's a shadow there because light finds it very difficult to go past a black hole. It gets bent because of the extreme gravity in the neighborhood. And this particular supermassive black hole is absolutely enormous, 6.5 billion solar masses. It's a very big galaxy with a very big supermassive black hole at its center. And imaging it is one thing. Okay, we seem to have this donut, which does indeed look like an accretion disk, but trying to understand why it has the shape and size it does and what's that shadow in the middle, well, again, simulations help us understand what it is we're looking at. An accretion disk seen from above looks just like a pancake. but an accretion disk seen from the side looks rather odd. It doesn't look like Saturn's rings as just a line, because the extreme gravity around the black hole means that although in principle this disk is just a disk, we can actually see the back of the disk because the light is being bent as it tries to get past the black hole on the way up, if you like. Not only that, not only can we see the back of the disk, we can see the underside of the disk as well, for the same reason. Light from that point on the bottom of the disk is getting bent by the black hole and is coming in our direction. So it's a rather odd-looking thing, but remember that's just distortion because of the black hole, not because it actually looks like that. It is just a disk structure, but it gets distorted by the gravity close to the black hole. And you can see that because this thing is actually rotating, it looks a little bit brighter on one side than the other, and that's why we get these variations in brightness in the accretion disk seen by these telescopes. At the time they took this data from the galaxy M87, they also took data from our own Milky Way. The center of our Milky Way, being that's the galaxy in which we live, of course is a lot closer than the center of a galaxy that is a long way away. But our Milky Way has got a much smaller black hole. It just happens to be a lot closer. And so in terms of how big does this appear in the sky, well, tiny, but it's roughly the same size as appears in the sky as M87. And they also took data from the black hole at the center of our own galaxy. Again, it shows the donut. Again, it shows some variation in light intensity. Looks a little bit different from the M87 black hole. Remember, this one is only 4 million masses, but is a lot closer, and so it appears bigger in the sky. But again, trying to understand these bright hotspots. It's a little more tricky to do the experiment for our own Milky Way. Even though it's smaller and closer, we have to worry about the fact that the matter is rotating around the black hole even faster because it's a smaller black hole than it would be for the more distant M87. So you can't simply take data all night and then see what you get, because that will blur out the sort of detail that they're trying to get. So in terms of data acquisition, it's a bigger problem to get the data on short time scales so that you can see whether or not these objects are actually moving as the accretion disk rotates. And although they appear the same size in the sky, because the donut, the accretion disk from our own galaxy, is smaller but closer, if we were to put them on the same scale, then there's the accretion disk on the left from the M87 galaxy, and you can see that it's huge compared to our solar system. That circle there represents the size of Pluto's orbit, so the accretion disk is much, much, much larger than the size of our solar system, if you define that as the orbit of Neptune or Pluto. The dot just tells you how far Voyager 1 has got so far. And we would have to zoom in right into that central region in order to see on the same scale the accretion disk from our own black hole, because it is large compared to the size of the Sun, but you can see it actually fits within the orbit of Mercury if we were to place it at that same position. So a huge difference in size, but similar in terms of data acquisition just because of the different distances involved. To give you an idea of just how powerful these jets can be, and we still don't understand how, we still don't understand why these jets form, we still don't understand all of the details of how these jets accelerate particles to produce the cosmic rays which are hitting the Earth all the time. Here's an illustration of just how massive these jets are. This is a visible picture taken by the Hubble Space Telescope of the galaxy called Hercules A. That's it in the middle there. And just by coincidence, there happens to be a small galaxy next door. We don't know, but that galaxy appears to be about the size of the Milky Way. It's a small spiral galaxy, which is probably about the size of the Milky Way. So that gives us a sort of yardstick as to how big Hercules A is. It's much bigger, it's less structured. It doesn't appear to be a spiral galaxy, but it is quite large compared to the Milky Way. But when we switch from visible light to radio light and actually see what radio waves are telling us about the jets that are forming, we think there's a supermassive black hole right at the center which is producing jets. And those jets don't just travel a short distance within the galaxy. Those jets are absolutely enormous. The jets travel for millions of light years. and they produce shock waves when the jets reach intergalactic space and collide with the intergalactic medium. So you can see that the shock wave itself is many, 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 many times bigger than our own galaxy. And yet that appears to be generated from the supermassive black hole, which on a scale, remember, is only the size of the solar system. Tiny compared to the size of our galaxy, tiny compared to the size of the jets that you end up with. Understanding the physics of exactly what is going on here and why is still an active area of research. We know that supermassive black holes are not exactly everywhere, but we know there are lots of them that are very active. If a supermassive black hole is feeding voraciously, in other words, if there's lots of matter falling into that black hole, if it's eating a lot of neighboring stars, if it's eating a lot of neighboring gas, then a lot of energy is being released. And in that case, we call these things collectively active galactic nuclei. And the most energetic ones are called quasars, a very useful label. Quasars have been known about for many decades because the most energetic galaxies were the ones that were easily detectable many decades ago. Some of these are so bright that even if they are at tremendous distances, you can still measure these things. So for instance, during lockdown, I set myself the challenge of can you actually pick up the light from one of these quasars on the other side of the observable universe, even without a telescope? I decided to follow Stephen Hawking's adage, remember to look up at the stars, not down at your feet, during the COVID pandemic. And yes, with a camera on a tripod, I managed to pick up a quasar which is 25 billion light years away on the other side of the observable universe, but it's producing so much light because it's a quasar, because it's a supermassive black hole producing an enormous amount of energy, you can pick it up even though you haven't got a telescope. Admittedly, it's not the most spectacular of images, it's just a pixel, but think of where that light came from. That light has been traveling for most of the age of the universe, and that quasar is now 25 billion light years away. So we know these things are very energetic, and we don't really understand why. We know there's a relationship between the size of the black hole and the size of the galaxy in which it sits. This is a logarithmic scale, but that doesn't really matter. The size of the black hole on the vertical axis and the size of the galaxy in which it sits on the horizontal axis. So there's the Milky Way down there, a reasonably sized galaxy with a reasonable sized black hole of a few million or so. But the real monster galaxies like M87 are up there at the top there. Really big galaxies with really big black holes. Now, it's not a perfect straight line, but there appears to be a relationship between the size of the galaxy and the size of the black hole that's resident at the core of the galaxy. But that doesn't answer the question, which came first? It's a chicken and egg problem. Did black holes start to form and then the galaxies form around them? Or did galaxies form and then somehow black holes start to form at their center? We don't really understand. Perhaps they went hand in hand, but that's one of the things that the James Webb Space Telescope is trying to answer. If you look back in time far enough, can you find a situation where you have galaxies that don't appear to have black holes, or can you detect whether or not you have black holes that don't appear to have galaxies around them? The James Webb Space Telescope has pushed back the boundaries to how far back in time we can go, and the question is, we don't yet know. It looks like supermassive black holes have existed very early on in the universe, implying you didn't have to wait until galaxies formed and then wait a few billion years for black holes to form at the center. It looks like black holes have been there, supermassive black holes have existed right from the off, and trying to understand how that can be is another big question in astrophysics. Final section, the C of the ABC, is collisions. Collisions dominate the way galaxies evolve with time. When we look at a picture like that, we can say, wow, what a pretty picture, isn't that beautiful? But of course, it can give us the impression that not much is happening. We know that some stars are being born in there, and maybe some stars are dying in there, and we know that the galaxy is rotating. It might take 100 million years for the galaxy to rotate. We can't sit and watch it, that's too boring, but we do know that they are rotating. But a picture like that can give us the false impression that everything is beautifully quiet and peaceful and serene when we look at individual galaxies. But of course, we now know a lot of the evidence has come from the Hubble Space Telescope over the last 30 years. When we look at lots of galaxies, we find more and more and more of them that appear to be interacting with their neighbors. Although we tend to think of galaxies as being in isolation, there is plenty of evidence that lots of galaxies interact with their neighbors. They just, for whatever reason, happen to get a little too close to their neighbors. Perhaps gravity is pulling them together. Perhaps they just coincidentally appear to be passing in the night, as it were. They get too close, and the gravity of one starts tugging on the stars of the other. So we know that interactions are very important. There's the Rose galaxy again, with what perhaps should be a nice spiral galaxy getting completely disrupted by its immediate neighbor. And we can tell from lots of pictures like this that galaxy interactions happen. But we can only really understand the influence of interactions between galaxies, and indeed we can only really understand the influence of collisions and mergers between galaxies by running simulations to say, what if? What if we have a lot of galaxies? How do they behave? And then we're back to the illustrious calculations again. So this is the very early universe, a different scale to before. We're not looking at one galaxy, we're looking at lots of galaxies, and it's absolute mayhem. It is absolutely galaxy soup. Notice there's a big galaxy coming in from the top and another big one coming in from the bottom. They are getting very close. They've just passed each other. They're interacting with each other. They've just passed each other again, and now they're merging together. So we've just seen two galaxies merge together into one mega galaxy, and we still have hundreds, if not thousands, of smaller galaxies around them. Let's just run that simulation one more time. So this is, again, over billions of years, because galaxies don't move that fast, but we have to remember that it's absolute chaos there. It is not the serene situation that we might assume by looking at individual pictures of galaxies now. Especially in the early universe, the galaxies were so close together that they were continually interacting with each other. There's a big distortion going on there of one being tugged on by another, and galaxies merge together. That's how galaxies grow. They're cannibals. They eat each other. Large galaxies gobble up smaller galaxies. Our Milky Way has probably eaten other galaxies. We are currently surrounded by lots of small galaxies, and we will certainly eat those in the not too distant future. One question we can ask with the simulation is, this seems to imply that we should see big galaxies with lots of smaller galaxies around them. Is this what we see? We look at the Milky Way, we see it surrounded by dozens or hundreds of smaller galaxies. So that does appear to be what we would expect. We look at other galaxies, we can't always see the smaller ones because they might be too faint, but we certainly see the ones around us. Also, we notice that when we look at galaxy clusters, this is a genuine color image in the sense the colors are real, not the false colors that we sometimes get on images. So galaxies that appear to be spiral galaxies, some of which you can see in the distance, quite often appear to be structured and quite often at the blue end of the spectrum. Whereas the large fuzzy ones in the foreground here tend to be more orangey and tend to be more like rugby balls, so-called elliptical galaxies. That can be understood if we assume that when we have lots of galaxies in a cluster, they're crowded together, they're much more likely to collide with each other, they're much more likely to grow because of the cannibalism effect of one galaxy eating another. And when galaxies collide with each other, they tend to lose their spiral arms and they end up looking like elliptical rugby balls rather than beautiful spirals. So that's why when we look at a lot of clusters, when we look at a lot of galaxies in clusters, they tend to be these rather amorphous blobs rather than lots of collections of spiral galaxies. And we are fairly sure that the Milky Way galaxy is going to collide with the Andromeda galaxy. Not just yet, don't panic. It's going to be quite a few billion years before it happens. But in about 5 billion years or so, the Andromeda galaxy is going to collide with the Milky Way. They are going to pass through each other. Very few stars are going to be impacted. They will initially move through each other and out the other side and completely disrupt each other. They will start to lose their spiral arms after a little while, and then after a little bit of toing and froing, after a little bit of a dance, they will eventually settle down to one mega galaxy, essentially gobbling up all of the stars that were originally in the Milky Way or in the Andromeda Galaxy. You can see that's going to take a while. It's going to take some 5 or 6 billion years for that to happen. So at the moment, when we look out into the night sky, we see the Milky Way from the inside, of course, and the Andromeda Galaxy is a nice target for astrophotographers. With a telephoto lens, you can get a lovely image of the Andromeda Galaxy. But if you're prepared to wait, the Andromeda Galaxy is going to get larger and larger in our skies. And by the time you wait for 3 and a bit billion years, the Andromeda Galaxy is going to be so big, you don't need a telephoto lens to get a nice picture of it. You would need a wide-angle lens. It's going to be that large in our sky. So for any astrophotographers, just wait a while. You'll have a fantastic photo opportunity. It won't take that much longer before the Andromeda Galaxy actually ends up crashing into us, at which point you will not be able to tell which star was originally in the Milky Way and which stars were originally in the Andromeda Galaxy. They will get completely and utterly scrambled together. There will be an absolute riot of new star formation because the collision of galaxies is not apocalyptic. It is not the end of life of a galaxy. If anything, it's the start of a new life. Because when galaxies collide, all of the gas of one collides with the gas of the other. Individual stars probably don't collide, but the gas does, and that triggers a whole new era of star formation. So all of these pink regions here are new star-forming regions. So when they are halfway through passing each other, there will be a whole load of new stars being born. Temporarily, they'll pass through each other and come out the other side. So there'll be a short period where the remnants of the Milky Way and the remnants of Andromeda have separated, but then, as we saw in that simulation, they will eventually settle down and merge together. After 5 billion years or so, the merger hasn't quite finished because we still seem to have a core here and a core there, as if we've got a galaxy with 2 nuclei, 2 centers. That's because the supermassive black hole of the Andromeda Galaxy and the supermassive black hole of the Milky Way won't merge with each other instantly. They will probably orbit each other for probably a few billion years before ultimately they eventually merge together themselves. And then we will genuinely have one mega galaxy which resulted from the Milky Way and Andromeda. What's its name going to be? Because we can't call it the Milky Way anymore. We can't call it Andromeda anymore. Would it be Milkdromeda? Would it be Andrilke? Would it be Androay? This is one of the most important things we have to decide, and we've got 5 billion years to figure it out as to what we're going to call this new structure once these 2 galaxies have merged together. If we were to wait long enough, every other galaxy in the local group, every other galaxy that's close to us, M33 in Triangulum, the Large and Small Magellanic Clouds, the dozens, if not hundreds, of small galaxies that are currently floating around, all of them will get gobbled up by this mega galaxy if we wait long enough. It is quite possible that when these 2 galaxies pass through each other, both supermassive black holes are going to start feeding voraciously, because they will have lots of material falling into them. Lots of gas, lots of stars will end up getting eaten by those central supermassive black holes, even before they merge together as one. So perhaps the Milky Way merging with the Andromeda Galaxy is going to turn our galaxy into a quasar. Remember, a quasar is bright enough to be seen from the other side of the observable universe. So there's going to be probably an enormous amount of energy pouring out of our galaxy when this merger happens. It's going to be bad news if the Earth is still around at this point, having survived the sun going through a red giant phase. We don't want to be anywhere near the core of this galaxy because it is going to be a real hotspot for energy production. But again, we've got 5 billion years to figure out what we do about that. So the ABC. A is for accretion. That's how they get born in the first place, from matter accreting. B is for black holes, which appears to be at the center of every galaxy, but we don't really understand why. How did they form so early on? such that even the very earliest galaxies that the James Webb Space Telescope is capable of seeing appear to already have supermassive black holes at their cores. They must be important, but we don't understand why. And evolution of galaxies is dominated by the fact that galaxies are cannibals, and collisions and mergers determine how galaxies grow over time from small objects into the sort of object that we have at the moment, the Milky Way, and how they will change in billions of years to come. So next time you look through a telescope, or next time you browse through the Hubble Space Telescope catalog on the NASA web pages and admire these wonderful structures that exist out there, just give a thought to how they came to be, the A, B, C of galaxy evolution. Thank you all very much.